Let's talk about the different models, the different linear models of that we have of amplifiers. We have four different types, which each of these types have an input stage, and each of them have an output stage. And the input stages on these four amplifiers all look the same. The output stages, there are two different kinds of output stages. There is this one, which is here at the top and all the way at the bottom here, which is a Thevenin source, dependent Thevenin source, is a dependent voltage and an output resistance. And then there are these two, which are dependent Norton sources. So they consist of a current source and an output resistance. The input stages are all the same, but you can see a little bit difference in how we label them. So for example, pick a different color here, like this one and this one, we label the input stage as a voltage, and then this one and this one, we label the input stage as a current. But even though we have labels of current and voltage on the input and the output, of course, there's always voltage as well as current at both ends, okay? So the first one is a voltage amplifier. We measure a voltage at the input, and then we have a dependent voltage source, which depends on that input voltage. And then there's an output resistance, okay? So the voltage measure the input is amplified. Then we have the current amplifier, which measures a current at the input. And the current amplifier has a current source on the output, which is a multiplication of the current that's measured on the input. Now, of course, repeat again, even though it's a current that we are producing on the output, there will be a voltage as well, which depends on what resistance is attached to that current source. Then we have two that are a mix of voltage and current. So we have something called a transconductance amplifier, which measures voltage on the input, and it has a current source on the output. And it's called transconductance because the constant of proportionality, you take voltage multiplied by a constant, get current. That constant must have units of conductance, 1/ohms. So transconductance amplifier. The fourth one is the transresistance amplifier, where the input is a current, the output is a voltage, where there's a voltage source on the output, let's put it that way more accurately. And the constant of proportionality, well, you have current on the input multiplied by a constant equals voltage, and that constant must be equal to resistance, right? So we can take a little bit closer look at one of these amplifiers here, which is the voltage amplifier, and I'm gonna I cut off the ground here. So the voltage amplifier, we can attach something to it if we want, right? We can attach a input source. I'm going to call that VS and RS like that, okay? And now the voltage VI, in this case here, is going to be equal to the voltage division of VS between RI and RS. Times VS like that, okay? On the output, we can attach a load as well, or attach a resistor as well, which will be the load. Here's a load, I call it RL, like that. And so the output voltage in this case here, the output voltage is going to be VO is equal to the voltage on the voltage source. So the voltage on this voltage source divided between these two resistors. Okay, so that's going to look like this. The division is RL over RL plus RO, and then multiplied by AVO times VI. That says AVO there, times VI, like that. Now I have a relationship. I can plug in the VI I had over on the other side, and I can compute VO equal to VI times, let's say, RI plus, sorry, that's not VI, that would be VS, right? VS. IR over IR plus RS times AVO times RL over RL plus RO, like that. That's the relationship between input and output voltages. But, you know, I could just as well, if I wanted VO in terms of the input current, well, what is the input current? It's not really labeled here, right? But there is an input current here, which I can call little ii, and it's easy to get it. II is simply equal to Vs divided by Rs plus Ri, like that, right? So I can plug that in up above, and maybe I should just do that real quick and say, well, then it's equal to II. Let's see, how do I do that? II, how do I want to substitute that in? Vs is equal to II times Rs plus Ri. Does that then become II times Ri times AVO times RL over RL plus RO, like that, right? And you can keep working this. You can say, well, I'm not really interested in VO. I'm interested in what is IO, and you can go and do that calculation. So just because something is called a voltage amplifier doesn't mean that there isn't also, of course, current on the input and on the output. Here's a different kind of amplifier, one of the other four types of amplifiers. This is the transconductance amplifier. And you can see the difference here is that it consists of a current source on the output. Again, I can attach a source like that, RS, and I can attach a load over here, RL. And it could be that I'm interested in the output current, but it could be that I'm just interested in the output voltage, right? So I can go through the same process here and say, make that a lowercase vs, like that, like that. I could say again, you know, VI is equal to VS times that voltage division ratio RI over RI plus RS, like that. And then I go over on the output and say, well, what is VO? Well, VO, in this case here, it's equal to this current. Pick a different color. It's equal to this current here flowing through the parallel combination of these two, right? So it's equal to this. It's equal to, let's see, it'll be equal to GM times VI times RO parallel with RL, like that, okay? Okay, but maybe I am actually interested in the current flowing through the load resistor. So what is IO? And by the way, I can, before I move on to that, I can now substitute in VI from over here, right? And I get an expression of VO in terms of VS. But suppose I really was interested in IO. Well, let's see, IO is a current division between those two resistors of GM times VI. So IO, which is the current flowing through RL, is the current division. And that when we do current division, we do the same as voltage division, except with the conductances. So IO is then equal to the current, GM times VI, and then voltage current divided, sorry, 1 over RL divided by 1 over RL plus 1 over RO, like that. And again, I can plug in VI, so I get now IO in terms of VS. So you can do all these kinds of manipulations, and you shouldn't be worried about the fact that it's called current or voltage. You always get a current and a voltage on either end, regardless of whether that end claims to be a current measuring end or a voltage measuring end or a current outputting end or a voltage outputting end. Okay, so all of these different kinds of amplifiers are completely equivalent. All of these 4 types of amplifiers that you have right here are completely equivalent, and you can translate between them. You can figure when you want a start with a voltage amplifier, for example, the top one here, and you want to replace it with a current amplifier, for example, you want to start by saying, okay, well, the input resistance and the output resistance have to be the same. And then you have to figure out what should be the AS in order to give it the same output, okay? And there you can look at, what's the short circuit current on the output, and what's the open circuit voltage on the output, and you can match those up. And you've done this before in your circuits classes. You've worked out, how to translate between a Thevenin source and a Norton source, which is the current source. All right, so that was a quick introduction to the 4 linear types of amplifiers that we will be talking about in this